The bobble hits. How did I know that would happen? We all need a bobble hit.
That's too funny. Oh, yeah.
Yeah.
Yeah, baby.
Yeah,
Yeah.
man.
His name
Yeah,
Randy.
baby. Yeah. The bobble hits. Bring you Sunday night astronomy show. Hey, folks, we're back again. Good evening, everyone. Cut it off, Paul. Okay.
That was a name.
No, that was me. I was bringing it up on Facebook, but I can't shut the speaker off till it comes up. So.
Okay, and here we are. We're locked in Facebook again for my feed. So you guys get it on Facebook up, Mike?
Yeah, we're good.
Okay, perfect. Okay, well, welcome back, folks. Good evening, everyone. Welcome back to our Sunday night offering of Astronomy Outreach, the Sunday Night Astronomy Show. First of all, welcome back our two regular co-hosts, Royal Astronomical Society of Canada member, Mr. Paul Owen from the dark, cloudy skies of Hampton, NB. Evening, Paul.
The dark skies in the city.
Outside, outskirts. And Royal Astronomical Society of Canada bobblehead there, Mr. Mike Powell from the PFO Observatory in St. John. Hey. Welcome. Okay, well, we've got another busy show here for you tonight. I'll be starting us off with another Where Are They Now segment. Tonight's talk will be the final discussion around the amazing 45-year mission of the Voyager spacecraft, 45 years so far. Tonight we'll talk about what is being called the Voyager Interstellar mission. Also on tonight's program, the biggest celestial event of the year, the partial solar eclipse, is just 1 month away, tomorrow. Of course, we can't view the eclipse safely unless we protect our eyes. So tonight, Paul is going to discuss some of the safe ways we can do that and get the best views possible. And as well, he'll do have another Rosanna's Interesting Fun Facts episode to share with us. Also, Mike's going to bring back Bino Bud and his share as another binocular target of the week. Blah, 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 blah. Okay. And we'll have all your wonderful photos, submissions to share as well. So sit back and enjoy. Remember, this is a family-friendly live broadcast, so if you have questions about the night sky, we're more than happy to try and answer them here for you. So let's get started, I guess, with another look at our segment, Where Are They Now? Where are they now?
Where'd they go?
Where'd they go? Okay.
No.
Sorry, we're having trouble playing this video.
Where's the beef?
Okay, let's start with share my screen. Yes, first off, entire screen. We're going to go with this one and share. And we're going to go to full screen. I know you guys are welcoming people on my behalf because I can't see anybody posting on Facebook at the moment. I can start to see YouTube though. It's good. Take a look at this first of all, I guess. This is our... oh no, we're not going to talk about that one yet. Sorry, wrong screen. Where's the other one? Oh. Hang on. Did I close that one? Oh, I did. Oh, just bear with me for a second. I'm going to try to open up something else here.
Sorry.
I'll bring this over here out of the way. We're going to go to this page. And I think I can get it from here. Maybe. Mission status. There we go. Okay, here we go. Let's try this one. Is that one coming up?
Yes.
Okay. All right, this is the Voyager 1 and 2 live data from the Voyager 1 and 2 spacecraft. So mission elapsed time, 43 years, 8 months, 4 days, 10 hours. Crazy. Distance from the Earth right now, they're looking at 14.1 billion miles. These are in miles. We can change that, I think, to metric. We can right here. There we go. This is just a website that JPL puts up for stats about the Voyager spacecraft. So They're now 22 billion kilometers away. Voyager 1 and Voyager 2 is 18 billion kilometers away. Look at how fast this number is changing. And that's distance. Actually, this one's going backwards. And that's because we're rotating around the sun and we're catching up to Voyager, actually. Voyager is actually going out at 35 degrees below the ecliptic plane, but we're actually catching up to it where its position is relative to us. So this number will go backwards at some time, and so will this one, but this one's actually going forward right now. But you can see how quickly the kilometers are strolling by there. Traveling at about 16.9 kilometers per second, which will be traveling forever now. One-way light time, so when we send a message to Voyager spacecraft, it takes 21 hours, 4 minutes, and 28 seconds to get a message there at the speed of light. Cosmic ray data we're looking at here, we can see that the cosmic rays coming in from the universe into our solar system are much higher. It's measuring a much higher level than it is from those that are pushing out from the solar wind. So we can see that they are truly in interstellar space. Now, they haven't passed the Oort cloud yet, but we're going to talk about that in a little bit. Here's the systems that are still running on the spacecraft. Cosmic ray subsystem, lower energy charged particles, magnetometer, a plasma wave subsystem. And it doesn't really tell us when they're going to quit, but we're thinking about 2025. Okay, that's that one. Let's get back to the presentation part, though. If I can close that window. And I'm back over here, and I got to go to this and this. There we are. I need to drag my window down the other way. Boy, the stuff you got to do. Okay, so where are they now? All these other spacecraft we'll be talking about in weeks to come. But of course, we're just talking about the Voyager spacecraft. Part 1 was week 1 overview and spacecraft position. The second one was planetary voyage, and this one is actually called the Interstellar Mission. So a little bit about the Voyager here. We're going to lead into it.
This is a Voyager Mission Control Area. This is where we talk to our spacecraft. Tonight we're going to be getting the data back from a magnetometer roll calibration maneuver. And that maneuver actually happened on the Voyager 1 spacecraft more than 16 hours ago, but the data is finally making it back to the Earth. What we're doing is a roll about this high gain antenna. And so if the high gain antenna here is pointed out toward the Earth, we're going to be rolling the spacecraft along that high gain antenna. That roll is done so that we can calibrate the instrument so that when we take data, we know what magnetic field belongs to the sun and what component belongs to the actual spacecraft.
Voyager 1 is now 120 times as far from the sun as the Earth is. That means it's 11 billion miles out, and Voyager 2 is 9 billion miles out. They're very near the edge of the bubble the sun creates around itself called the heliosphere. We're getting very close to the boundary. We don't know how close because no spacecraft has ever been there before. But it could be another few months, it could be another few years, but it's probably not much longer than that. We travel 1 billion miles every 3 years. You can't see the bubble the sun creates around itself because it's invisible, but we can see an analog of it in a sink. If we turn the water on very fast and look at the bottom of the sink, we see that near where the water hits the bottom of the sink, it's flowing very fast radially outward in all directions and getting thinner until it abruptly slows down in this thick region and turns around and flows down the drain. The two Voyager spacecraft are both in this thick region in our heliosphere where the wind has slowed down and is turning to go down the tail of the heliosphere. And eventually, within, we hope in not too many more years, Voyager 1 will leave this thick region and enter interstellar space. It's really remarkable. We have a 20-watt transmitter on the spacecraft transmitting over 11 billion miles away. And so it comes in very slowly. But every bit left that spacecraft over 16 hours ago. Every bit is telling us something new that we haven't known before.
And so that video is about 5 years old. So it's actually traveled much farther than that now, 21 billion kilometers out. Travels 3 billion kilometers or 1 billion kilometers over 3 years. So it has traveled quite a bit farther. So the mission objective of the Voyager interstellar mission was really to extend NASA's exploration of the solar system beyond the neighborhood of the outer planets to the outer limits of the sun sphere of influence and beyond. Now, the VIM is an extension of the Voyager primary mission that was completed in 1989 with the close flyby of Neptune and the Voyager 2 spacecraft. Neptune was the final outer planet visited by a Voyager spacecraft. Voyager 1 completed its planned close flybys of the Jupiter and Saturn planetary systems, while Voyager 2, in addition to its own close flybys of Jupiter and Saturn, completed close flybys of the remaining 2 gas giants, Uranus and Neptune. At the start of the VIM, the 2 Voyager spacecraft had been in flight for over 12 years, having been launched in September of 1977. The Voyager 1 was at a distance of approximately 40 astronomical units, and Voyager 2 was at a distance of about 31 astronomical units, and 1 astronomical unit is 150 million kilometers from the Sun. It is appropriate to consider the VIM as 3 distinct phases: the termination shock, the heliosheath exploration, and the interstellar exploration phases. Now, the 2 Voyager spacecraft began the VIM operating in an environment controlled by the Sun's magnetic field, with the plasma particles being dominated by those contained in the expanding supersonic solar wind. This is the characteristic environment of the termination shock phase. At some distance from the Sun, the supersonic solar wind is held back from further expansion by the interstellar wind. The first feature encountered by a spacecraft as a result of this interstellar wind interaction was the termination shock, where the solar wind slows from supersonic down to subsonic speeds, and then large changes in the plasma flow direction and magnetic field orientation occur. Voyager 1 is escaping the solar system at a speed of about 3.6 astronomical units per year, 35 degrees out of the ecliptic plane to the north, in the general direction of the solar apex, or the direction of the Sun's motion relative to nearby stars. Voyager 2 is also escaping the solar system at a speed of about 3.3 astronomical units per year, 48 degrees out of the ecliptic plane to the south. A passage through the termination shock ended the termination shock phase and began the heliosheath exploration phase. The heliosheath is the outer layer of the bubble the Sun blows around itself. It is still dominated by the Sun's magnetic field and particles contained in the solar wind. Voyager 1 crossed the termination shock at 94 astronomical units in December 2004, Voyager 2 at 84 astronomical units in August of 2007. After passage through the termination shock, the Voyager team eagerly awaited each spacecraft's passage through the heliopause, which is the outer extent of the Sun's magnetic field and solar wind. In this region, the Sun's influence wanes and the beginning of the interstellar space can be sensed. It is where the million-mile-per-hour solar wind slows down to about 250,000 miles per hour, the first indication that the wind is nearing the heliopause. Now, before Voyagers could pass through the interstellar space, they needed to ride the magnetic highway. Now, here's Dr. Ed Stone, project scientist for the Voyager mission, explaining that process. And he's going to explain it here soon. Here it is.
Voyager 1 is in a place no spacecraft has ever been before. We are in the very outer edge of the heliosphere, on magnetic field lines which act like a huge highway, so that all the particles that were inside the heliosphere have streamed away and are now gone, and what we see instead are the cosmic rays from the outside interstellar space which have streamed back in to replace them. For the last 7 years, Voyager 1 has been in a region of the outer heliosphere where it's surrounded by ions, moving at about a few percent the speed of light. Those ions were accelerated in this region and are moving uniformly in all directions. As Voyager 1 continued, though, it began to see a change in that distribution and entered a magnetic highway where all the pink-colored ions were leaving the heliosphere along the magnetic field, and at the same time, the blue ions, which are the cosmic ray particles moving with a higher speed, started coming in from interstellar space. Voyager 1 is now in a region where it's surrounded only by the cosmic rays accelerated elsewhere in the galaxy.
So on August the 25th, 2012, Voyager 1 flew beyond the heliopause and entered interstellar space, making it the first human-made object to explore this new territory. At the time, it was a distance of about 122 astronomical units, or about 18 billion kilometers from the Sun. Now, this kind of interstellar exploration is the ultimate goal of the Voyager Interstellar mission. Voyager 2, which is traveling in a different direction from Voyager 1, crossed the heliopause into interstellar space on November the 5th of 2018. Now, of course, all of this data wouldn't be even available if it wasn't for the amazing people at the JPL and Deep Space Network, those receivers here on Earth that pick up the Voyager's feeble signal. Let's take a quick look at their operation.
Deep Space Network is basically required to do the kinds of things that we do in space.
Clearly, if you can't talk to your spacecraft and they can't talk to you, there's no point in even sending them out there. The Deep Space Network makes everything that we do possible. Imagine landing night, for example, for Curiosity without the Deep Space Network. There'd be no one in there because there'd be nothing to see. We would hear nothing from the spacecraft. No touchdown confirmed, no cheering, no nothing. The Deep Space Network is what helps us figure out where the spacecraft is. We wouldn't even get close to Mars without it.
The Deep Space Network comprises of 3 complexes around the world, placed about 120 degrees apart. This ensures us that we are constantly in touch with the spacecraft as the Earth rotates. We're today tracking 33 spacecrafts, not only the US spacecrafts, all sorts of spacecrafts from other countries. And remember, this is not only talking to the spacecraft. We have been able to do radar and radio astronomy. And it was the radar on this antenna that actually was used for even the men landing on the moon. 50 years ago, director of JPL, Dr. Pickering, and NASA established the Deep Space Network to provide communications for all the deep space missions, rather than having each of the missions build their own ground network.
We used to use big analog recorders for telemetry signals. We used a 2-inch wide tape. In the beginning, the first computers we put in, we had 64,000 words maximum. And we had to be able to support every mission, NASA missions, other foreign missions, and digital technology and computers allowed that to happen.
If you look at the Cassini mission, we've got a transmitter about an average of 800, 900 million miles away. The transmitter is about the power of your refrigerator light bulb. And that is what is bringing all these incredible images and data back. I think it's a resource to be treasured, but it's a resource that also needs to be nourished.
We are looking at missions with higher data rate, more complicated missions with more instruments on the missions. We are looking at optical comm. And with optical comm, one day we should have streaming videos. You can see real time rather than a simulation.
Seeing our success in almost real time and knowing right away and seeing those pictures, all possible because of the DSN.
If there was no DSN, there would be no missions. We always remind the missions, don't leave the Earth without us.
So as stated, the 3 installations for the DSN are located at 120 degrees from each other around the globe. Now, since Voyager 2 left below the plane of the planets, only the dish in Australia is able to talk with it. And here is the radio signal of Voyager 1. Next one up. Here's a radio signal of Voyager 1 captured by a radio telescope here on Earth from over 20 billion kilometers away. That little dot back there is when it was sending back its signal. Now, how amazing are these people, their instruments, and the spacecraft? Well, for example, for the past 40 years, Voyager 1 has been using its attitude control thrusters to keep the spacecraft antenna oriented to Earth so that it can communicate with us and us with it. Now, the thrusters fired tiny little pulses lasting for just milliseconds. Now, from 2014 to 2017, they were degrading, and that was worrying the Voyager team. While propulsion experts at JPL considered different interventions and how the spacecraft might respond to them, they proposed attempting to start the 4 thrusters located on the back of the spacecraft, hoping they could take over the control of correctly orienting Voyager. In the early days of the mission, these thrusters were used to keep the probe's instruments targeted on Jupiter, Saturn, and their moons as the spacecraft flew by them. While they pored over decades-old data and deciphered outdated software code to make sure they could attempt to turn on the TCM thrusters without causing damage to Voyager. Then the engineers fired them up and tested their ability to orient the spacecraft. They had to wait 19 hours and 35 minutes for the data to make it back to Earth, but eventually they got the good news. The thrusters were up to snuff. The plan was to shift the orientation work to the TCM thrusters each required a heater to operate, and turning on the heaters requires power, which is a strain on the aging probe. But the maneuver worked, and Voyager 1 is now back on track. So they didn't fire for over 40 years, and they lit them, and they worked. The engineers will likely attempt the same move with Voyager 2. As the twin crafts fly deeper into the universe at more than 36,000 miles per hour, they will keep talking to Earth for at least a little while longer. And they did try the same technique with Voyager 2, and it worked as well. And how did Voyager communicate that it worked? It sent back a signal at the strength of 28 watts. But by the time it arrived here on Earth, it was only one quadrillionth of a watt. That's a 1 followed by 16 zeros. Now, Pioneers 10 and 11, which preceded Voyager, both carried a small metal plaque identifying their time and place of origin for the benefit of any other spacefarers that might find them in the distant future. With this example before them, NASA placed a more ambitious message on Voyager 1 and 2, a kind of time capsule, intended to communicate a story of our world to extraterrestrials. The Voyager message is carried by a phonograph record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture here on Earth. Now, here's a quick interview with producer of the Golden Record, Timothy Ferris.
تحياتنا للأصدقاء في النجوم.
Hello from the children of planet Earth.
I'm Timothy Ferris, and I produced the so-called Golden Record on the Voyager spacecraft. Sometimes people say, well, nowadays you could put a lot more information on, the equivalent of a DVD or something, but we don't know how long optical media will last. We know how long grooves in metal last because we have a lot of historical record for that. In fact, the origins of writing are recorded in Sumerian cuneiform, which are gouges made in clay, and they're very stable for long periods of time. So if I were making the Voyager record again today, I would make it the same way. I would make an analog record because I know it'll last 1 billion years. It can last 1 billion years. Of course, it might have been a little harder to master the record now than it was in 1977 when people were still making records.
So from there, the Voyagers have enough electrical power and thruster fuel to keep its current suite of science instruments operating until about 2025. By that time, Voyager will be about 22.1 billion kilometers from the Sun. Voyager 2 will be about 18.4 billion kilometers away. Now, eventually, the Voyagers will pass other stars. In about 40,000 light years, Voyager 1 will drift within 1.6 light years of AC plus 793888. A star in the constellation of Camelopardalis, which is heading toward the constellation Ophiuchus. In about 40,000 years, Voyager 2 will pass 1.7 light years from the star Ross 248, and in about 296,000 years, it will pass 4.3 light years from Sirius, the brightest star in the sky. Now, there's nothing to cause a rate of decay on the spacecraft. Long after our Sun has become a red giant and engulfed the Earth, these two spacecraft could be continuing on their 250 million year journey around the Milky Way. The Voyagers are destined perhaps for eternity to wander the Milky Way and to carry with them the last remnants of a civilization once known as human beings on a tiny world called Earth. Oh, sorry, wrong Voyager. Oops. And that's my presentation.
You gotta love those little cartoons at the end.
Yeah. Anyway, yeah, out there for billions of years.
That's unbelievable, isn't it?
Long after the sun has become a red giant and swallowed the planet Earth, and our sun has just become a white dwarf, these things will still be out there. And I mean, civilization may be long gone by that time, but that's our only testament to that we were ever here in the first place, right?
Yeah, exactly.
Yeah.
I often think, about this whole time comparison thing, and it kind of blows me away. Sometimes you go walking through a cemetery, and then you look at a gravesite that's 100 years old, and then you look at the dates that are on that grave, on that tombstone, and let's say it was, I don't know, 80, 90 years back in those days. They only lived to be 60. But think about how short a time we are here.
Yeah.
When you think about in relation to that, it's just anyway. That blows me away.
It introduces humility, and that's the whole thing about astronomy that I enjoy. It's that humility when you're looking up, right? And just thinking that these two little spacecraft are still out there 45 years later, still communicating every day back to Earth. And we're picking up that signal at 1/10 quadrillionth of a watt.
Yeah.
It's amazing that we can even talk to it. It's actually capturing it has like an 8-track tape player on it. And it plays one frame of tape. That's what it sends back every day. I mean, there's not a whole lot happening with it right now. All the fantastic stuff has already passed. But to still know that we're still talking with it, it was only supposed to last 5 years. Now it's 45 years later. Well, just
But just the fact that you can travel in one direction for
forever.
45 years.
Yeah, forever at the same speed. Yeah.
Yeah.
70 kilometers every second. Yeah, for 45 years. Amazing. Okay, let's move on from that to. That's my talk on Voyager. I'm glad I did that talk because I was looking forward to doing that one because that's the one that brings the biggest amount of humility to me, I think. So let's move from there to solar eclipses and safe viewing of the sun. So, Paul.
Stuff. More stuff.
Okay,
More stuff.
I'm going to just offer that little quick view of that.
Yes.
Okay, so it was. I think I had it right here somewhere. There it is. Okay, so here's a little quick view of what it will look like on the morning of June the 10th at 5:30 a.m. So as the sun rises at 5:30, the moon will move in shortly after. And this will be our view from St. John anyway. It's about 73% eclipsed at maximum eclipse. And then the moon moves off. And by 7:36, the eclipse is over. So that's what we get to see.
That would be totality to a degree. It's totality at that phase.
Right.
And then we get to see it go the other way.
Right. Yeah. Sliding in from that direction. So.
Yeah, it's always just amazing. Last time we did that, we were at I think you were at the beach.
Yep.
And I was down with Peter and Kurt. Phil down at Rockwood Park.
Yeah, we were inside the Irving Nature Park at the time.
It was on August the 17th, if my brain is any good at all.
21st of 2017.
Okay, I was close.
That was a great American eclipse that came across the country, and this one is actually going to come up the coast this way. Actually, that one goes up this way, then the one in 2024 that's coming over us April the 8th. That'll be amazing.
Right,
yeah. Okay.
Anyway, it was an event because there were so many people out, and boy, I miss that.
Yeah, it was a Saturday afternoon, wasn't it? Or
it
was a weekend.
I can't remember, to be frank, but if I was Bill, let's say.
This one's going to happen on a morning, like a weekday morning. So I think it's a Thursday weekday morning. So won't be quite the same crowd for sure. But.
No, for sure. But anyway, okay. So I guess I should get running here. So what I'm going to talk about tonight ties into what Chris was talking about, and that's the solar eclipse that's coming up. But that's not what the talk's about. The talk's about how can you look at those things, view those things safely, whether you're using binoculars, whether you're using a telescope, or whatever you want to look at that particular thing with. But not only that, but what can you actually look at the sun with because with the sun, there's so many things to study on the sun. And when you're studying the sun, you're also studying stars because the sun is a star. So when you learn all these cool things that you can see, or not so cool things that you can see on the sun, it's just absolutely amazing. You could spend your whole astronomy life just studying the sun if you wanted to. And anyway, it's pretty cool. So how do you do it safely, I guess, is what we're going to talk about. So I think what I'll do is I'll start by sharing a screen and see if I can pull this off correctly, because I'm that one, and it's going to be that one, and I'm going to share that screen, and I'm going to start out. Actually, I think I'll start out with Etiquette. So the first thing you're going to see there is a chart. In this chart, it says, how do you watch the eclipse safely? What to use? So, of course, you can use sunglasses, but they have to be specifically made for watching an eclipse. They are using the proper solar paper in these sunglasses. The same with the telescope or other lenses with special filters. And as Mike and I were talking about earlier, those special filters need to be on the front of the objective, not in the back. Never in the back, always on the front, with one exception. And I'll show you that a little later as we go through this. What not to use. So you don't want to use cameras looking at this. You don't want to use regular sunglasses. You don't want to use x-ray paper. You don't want to use mobile phone. And you certainly don't want to look at it with any optics whatsoever unless they are protected with the proper gear, the proper filtration. So there's 5 ways to view a solar eclipse. You can use, again, the special glasses. If you're going to use binoculars, you can get binoculars, or you can get solar filters that actually fit right on the face of binoculars. You can use a telescope with the same thing, and I'm going to show you these examples. Again, you got to have a special filter on the front of the scope. For an eclipse, you can use welder's goggles, but they have to be purchased from a welding supply company with a shade of at least 13 or 14. And it has to meet that requirement or they are not to be used. Or you can use a little pin. And you're thinking, how in the heck can you use a pin to watch the sun? Well, I'm going to show you that too. What you don't want to use, and Mike was so kind to show me this, and what this is one of those filters that actually screws on the front of an eyepiece. And these things, I think when he was looking at them, he was telling me that you can the instructions say you can only use it for 15 seconds. You can only use it when the sun is just coming up or just going down. And what were the other restrictions, Mike? Do you remember?
Not really sure right offhand, but that were the big ones. And the point I was trying to make is don't use it at all.
Exactly. Exactly. So this is one of those things that you do not use. So if you go on to Amazon or any of those places and you see something like this, ignore it because it is not your friend. You do not want to use that. You will probably have eye damage that will be irreversible. So again, we've already covered that. I'll skip through there. So that little pin that we talked about, that little pin that you put the diapers on with, or you hang stuff on the wall. Well, that little pin is designed to poke a hole in a piece of paper. And that's what you're looking at right here. So this one is what they call projection. So if you're looking at the sun, you can take some paper or cardboard, you put a little pinhole in the center of it, then you take it and you aim it towards the sun, and then you aim that towards a white sheet of paper, and then basically that will project whatever that you're looking at onto that paper, and depending on how far away you move it back and forth, you can actually make that image larger or smaller. So that's another very, very safe way that you can observe the sun. And I don't know if I would observe the eclipse totally that way because you'll probably not see a lot, but certainly the sun. I don't want to show you that. Okay, so before I show you this, I'm going to get out of this presentation because I want to show you something live here. And Chris, can you pin me?
Sure.
Or do I pin myself?
I can pin you right there. You're pinned.
Use that little safety pin to pin you, or
I've never used for it. Thanks, Mike. Okay, so what I want to talk about here are there are two types of paper, there's two ways of getting solar filtration. One is with solar paper, and you can buy solar paper from a company named Bader Planetarium, which is this company right here, and they sell the solar paper. And when you get it out of the package, what it's going to look like is going to look like tinfoil, but it's actually very well engineered solar paper. And it's designed to reject 99% of light. So when you're talking about the sun, 99% of light is a lot of light rejection, but there's still that 1%, which is still extremely bright. And what this paper does, or actually what I should say, the paper comes in two forms, visual and photographic. So if you were just starting out and you're going to get into either making your own filter or buying filters, my recommendation to you is simply this. Go with the visual paper, because with the visual paper, you can safely observe the sun whenever you feel like it. And at the same time, if you want to image with it, you will not have any degradation in your telescope unless you're using, a study grade telescope that you'll probably never ever use. Most telescopes that people buy are in what they call an F ratio between, say, 5 and even 20. That paper will work extremely well, both visually and photographically, between any of those f-stops. So that's what I would recommend to buy. The reason they have the photographic paper is for people who are doing eyepiece projections, where you're actually taking it almost similar to that little demonstration I showed you a second ago, where the light goes through the thing and you're making it bigger or smaller. You can see it like that, but the luminosity is considerably less. So when it's cut down that much, that photographic paper has a lesser neutral density value, so it allows more light to pass through. That's what you use it for. But most people aren't going to use it for that. So again, just get the regular photograph or visual paper, and that's what you want to buy. Okay, enough on the paper. Let's talk about the filters. Okay, so there is what we call a white light solar filter. You can buy them in a lot of different ways. You can buy them like this. You can buy them like I showed you. You can buy the paper itself, and there's actually instructions in here on how you can make your own just using cardboard and tape. It's very, very simple. Mike actually has made some with his printer. He's got a 3D printer, and he's made some with that, and they're fantastic. The key is good paper. The second key is good adhesion. You want to make sure that that filter is on secure. So the one that Mike made works extremely well, but it's actually designed specifically for a scope that he has. This one here you can use on a variety of scopes, and the reason you can is because it's got these little twisty neoprene little nuts on it, or bolts, whatever you want to call them. And so you can use this. This one is designed for up to about 6-inch telescope, down to about a 4-inch scope. So you can get about a 2-inch variance with these little screws in there. Very simple to use. It just simply goes on the front of your telescope, and away you go. In fact, just like this little one behind me. So basically, there's your telescope. This one's just a push on, but it's the same idea. So all you're going to do is you're going to take your telescope, and you're going to take this little filter once you've got it, and you've got the right size for your scope. And all it simply does is just slide over the face of your telescope. And that's it. Once it's on, you're safe and you're good to go. Now, that's what they call a white light filter. Now, let's talk about what you can see with a white light filter. I'm going to share my screen again. Okay. That one, and go. So what you can see with a white light filter, there's actually quite a few things you can see. I'm showing you a picture of the sun that I took back December the 3rd. Here it is, 2020. And this was one of those very few times that we had something to look at. There was actually some spots on the sun. And this was sunspot number AR2786. And this was taken with a white light filter. And I was using my Schmidt-Cassegrain telescope, which was an 8-inch telescope. And basically you just put the paper on the front, you aim it at the sun the same way you would aim it at the moon, the same procedures really. You might have to adjust your gain on your camera or whatever you're using to photograph it, but it's really the same thing. And in fact, the sun and the moon are both the same size according to your camera. So our view or our perception of the moon and the sun are the same. So if you've got a filter that works for the moon, or if you've got a scope that works for the moon, my apologies, then you can get a filter that'll work for the sun on exactly the same equipment, because again, they're both the same size as far as we're concerned. So that was taken with a white light filter. Now, one thing you may or may not know, the sun is not yellow. The sun is not green. The sun is not pink or purple. The sun is actually white. And what that white light filter does, that beta filter, it actually shows you the true color of the star that we call our sun. And so when you put that filter on, what you're going to see is not a yellow sun like I've got here. I actually colored that yellow. You're going to see white. It's going to be white, and if there's any surface design on it or any surface features on it, they're going to be black. So black and white is what you're going to be recording that in. And if you want to fill it in with color to make it look pretty, make it look like a pretty picture, which is what I did there. That's what you do. Okay, so that's white light filter. What you can see are these little guys. Now, these, of course, are called sunspots. And we're actually talking about this, I think, at the right time, because we're actually getting out of solar minimum. That's an 11-year cycle that the sun goes into where it just kind of almost goes to sleep. It doesn't do a whole lot of anything. Sunspot activity, all of those things, you virtually see hardly anything. Last couple of years, it was almost like a blank sheet every time people go look at it. So people got disinterested. Good time to buy a solar scope. But anyway, so what goes on with the sunspots, as you see here, is when you look at the sun through your telescope, you will actually see this. Take away the yellow. You will see this in white, unless you're using a glass filter. If you're using a glass filter, then you will see yellow. But most people are going to use the paper, which is going to give you the white light. And so what you're seeing there are sunspots on the sun. So this is one of the things that I find that would be very interesting to get involved with is the sunspots and the actual features on the sun. Because you don't want to just look at the sun for the sake of looking at it. Usually when you observe something, you want to learn something from it. And there's a lot of things that you can learn by using a white filter on your telescope when you're looking at the sun. So for example, when you're looking at the sunspots, the umbra, which is that little black spot right in the center, that's basically an area of the sun that's actually cooled down, and that's still at close to 7,000 degrees Fahrenheit in that hole. And what the sunspots are basically are just areas of the sun that mechanically they just they just sort of it's a magnetic portion of the sun. There's a magnetic release. There we go. And then what happens, there's a little spot in the center that cools. And when it cools down, of course, it gets darker. So they call that the umbra. Now, around that's what they call the penumbra. And the penumbra is just basically, it's an area, it's almost like a ring that goes around it. And it gives you that look. So you got the penumbra and the umbra on the sunspots. You can also get, and then what do they call them here? I actually had that written down. I was going to tell you that because I thought it was such a cool thing. And I'll probably not find it now. Yeah, what do you want? What have it? Okay, well, anyway, I'll find it later. But anyway, so there's they're just called spots. These little tiny areas here don't have a penumbra around them, and they get to be, the size of those, they're about 1,100 miles wide, which is amazing. But those little spots there, yeah, but they're so small that they don't actually get the penumbra on there. But anyway, so that's one of the things that you can see on the sun. Second thing with white light solar filter is you can actually see the granulation. So when you look at all that little rough surface, almost like the surface looking at the front of an orange, that's basically just all kinds of stuff that's sort of bubbling up on the sun. And in that granulation, each one of those can be close to the size of Texas. What's neat about those is they're continually changing. About every 5 to 10 minutes, they change. So it's just like watching a bowl of oatmeal bubble. That's kind of what's going on that portion of the sun. So you can see that granulation. You can also see those what they call facula, which is those whiter areas right here. So there's those three things just alone, just when you want to take a white light filter out and have a peek at the sun, you can see those. If, and I don't think this will work, it might, let me just see. Yeah, there it goes. So what you're looking at here is an actual video of taking a picture of a sunspot. This is what you would go through. You just take, instead of looking at your sun with your eyepiece, you pop in a webcam or a high frame rate camera, stick it in there, and then you just record video of the sun and of the sunspots. And once you got that, you just stack it like you would a moon picture, and there's your picture of sunspots. Very, very simple, very easy to do. Okay, so that's white light filters. Now let's get into another type of sun filter that's very, very easy to watch, or safe to watch, I'm sorry. And that's called hydrogen alpha. Hydrogen alpha is basically it's a band in a wide wavelength of light, and it's just a sliver. It's just like a small band at about 656 nanometers. I know that doesn't mean anything to you right now, but I think I have a picture. I can show you what that is. I think it's in here. There it is there. So if you look at this, when you're talking hydrogen alpha, what you're talking is right in about there. So this is the blue violet light. This is the bluish, almost bluish, starting to get teal light. Oxygen 3 hangs in and around there. Sulfur hangs in and around there. And then over here, you've got hydrogen alpha, which is that red light. Our sun, or the colors that we perceive it to be, would be in this yellow area here. But this is the area here that hydrogen alpha looks at the sun with. And what it does is it actually takes anything from this point back, you don't see it. Anything from this point forward, you don't see it. But when you have a telescope, it allows you to, or a telescope made for this, it allows you to kind of tune in and out by about 0.1 angstrom one way or the other, so that you can see various features on the sun in hydrogen alpha. So I just want to show you, when I talk about hydrogen alpha, what I actually mean. I'll get back. Whoops. So there's a picture of the sun that was taken with a hydrogen alpha scope. Now I'm going to take and show you, I'm going to take my screen off one more time, and I'm going to go back to me here, and I'm going to show you what a hydrogen alpha scope looks like. And it's right here. If I can get it out. So all it is just a very, very small telescope, very small. This one's only 60 millimeters, so it's not much bigger than a pair of big binoculars, really. And basically what it is there's a special lens on the front. There's a special blocking filter in the back. And it just looks like a little telescope, but it's designed specifically for the sun. So I don't know if you can see that. You probably can't, but I'll see if I can turn so you can. There. So you can see that the front of that telescope is very different. It's very dark. And again, it's because what they're using here on the front of that scope is very specialized and is tuned to a very specific light frequency. So that's basically a small little hydrogen alpha scope. So if you look at them, think, oh my gosh, such a small little scope. Can't be that expensive. Well, they're a little bit up there, but most of the astronomy clubs have one. And if you're ever a member of Astronomy Club, like we are with the St. John Astronomy Club, we have one and we lend it out to the members. So they're always available for through us. Okay, so let's go back to here again. And I'll fly through this because I'm getting short on time. So that's basically what you can see. So the things that you can see with hydrogen alpha that are different than white light filter would be these things right here. And these are what we call prominences. Prominences are basically gaseous areas that are just coming off the sun's surface. They're being released. And some of them typically will go out and loop right back in, but some of them will actually snap off and just go forward. And those are what you get your mass ejection from, the CMEs, the coronal mass ejections. And some of those things actually, if they're actually aimed at Earth at the same time that they let go, these are the things that come down and create our auroras, which is kind of cool. So if you want to see what that looks like in a camera, real life, that's video that I took a long time ago of this particular prominence. So this is really cool, but this, you can only get this if you have a hydrogen alpha filter telescope to be able to pull this off. So I had one and I was able to get the video of this. And then once I was done with the video, I was able to make a picture of it. So it's a very, very nice light to work with. Now, there's another picture I want to show you here. And this one is kind of the one that is a bit important. When I was telling you earlier about how you can alter by 1.1 of an angstrom one way or another, all that simply means is, let's just call it click, brighter or duller, if you want to say that. So on this side here, we're at 1 point angstrom. So that's going to give you that, when you look through a hydrogen scope, visually, this is what you're going to see. It's going to be in red. This is that 656 nanometer color. But what you can see when you see it in this color is you can see all those prominences, those things that I just showed you a minute ago in the video. You can see all of those things on the outside of the sun. If you tune your scope just a little bit by a half of an angstrom the other way, then those prominences will kind of go away, but all the surface detail becomes available to you. So now you can see prominences sideways, which are called filaments. You can see, again, sunspots. You can see all kinds of cool things on the sun just by the simple move of a lever. So it actually lets you tune in and out of various things on the sun. All of these things you cannot see with white light. So hydrogen alpha is what you would have to use to be able to see those things. All right, so let's just get down there. And I'm just going to go through really quickly. I'm not going to show you any of this stuff. I was going to, but there's only one thing I want to show you on this. And it's a very, very short video. If I can find it. If I can't, then we won't worry about it. Oh. Okay, we won't worry about it. And I'm going to go back to stop presenting. So those are the things that you can see. Now, before I finish up, I just wanted to just cover a couple of things that about solar viewing that you can do. So with the solar eclipse coming up, you can certainly watch that. That'll be a really nice event to watch. But it doesn't stop there. You can look at the sun anytime it's sunny out. Just get out there. If you have a telescope or a pair of binoculars or anything like that, more or less a telescope, you might want to see some of the features like sunspots on that, unless they're relatively large. But just get your white light filter, pop your white light filter on, go out and enjoy the sun. It's absolutely wonderful to learn about. And again, just remember that when you're watching and learning about the sun, you're actually watching and learning about all the stars that are up in the sky, because all those features that we talked about here, you can see on the sun. So remember to be safe with your viewing of the sun. Follow those things that we talked about earlier. If you want to play this video back, you can screenshot any of those things that are on there with all the do's and the don'ts. And it's something good to find, or you can look it up on the internet. As far as getting the paper to make your own filter or buying the filters, any astronomy manufacturer or retailer, you can buy it through. And I would recommend buying it through a retailer than somebody who sells stuff and they sell bread and everything else. Make sure you get it from somebody who specializes in it, because they will probably ask you some questions. What do you have? What are you going to do? And because they want to make sure you're safe too. So other than that, that's my chat on solar filters.
Well done.
I pushed it through pretty fast, so.
You did. But that's great. Good coverage there. And like to say, the number one thing is be safe with solar filters. Okay, we're going to move from there into Mike's Bino Bud Talk. Binocular Target of the Week. Great info, Paul.
Yeah, thanks. Can you, am I pinned? Oh, yeah.
No.
There we go. Sorry.
Okay.
Gotta move a window around here. There we go.
We are going to be just a few minutes long here, folks, tonight, so if you don't mind. What else would you be doing, right?
So, Bud should be up on the screen.
He is.
Yeah, he is.
I was originally going to do one object, and then I finally figured out after going through the presentation I had already done it. So I changed the object of the week, and thank you, Chris, for not writing up that I was going to do the other one. So, binocular target of the week this week is M13.
Where you get this stuff? I don't know.
We're going where? Messier 13, also designated NGC 6205, is sometimes called the Great Globular Cluster in Hercules, or the Great Hercules Cluster. It is a globular cluster of several 100,000 stars in the constellation of Hercules. Although only telescopes with great light-gathering capability can resolve the stars of the cluster, M13 may be visible to the naked eye depending on the circumstances, and it is very visible in a pair of binoculars. But where do I find it in the sky? Well, now it's starting to get dark. It's pretty much dark around 10:30, 11 o'clock now that the sun sets at 8:30. So around, let's say 11 o'clock at night, walk out, turn 90 degrees to the east, and look up. You'll see the bright star Vega, and not too far from you can say to the west of Vega or to the right-hand side of Vega, you're going to look for this keystone. It's the easiest part to see in Hercules is the 4 stars that make up this keystone. And when you look at that keystone and find it, you get in close. These are the 2 stars on the one side of the keystone that are closest to Vega. You want to look at the far side or the longest side. And M13 is either 1/3 from one direction on the stars to the other, or 2/3 if you go the other way between these 2 stars on the far side. Now, if you want to challenge yourself, there's also a second globular cluster in there. That's why I threw it M13. It's called M92. If you look at the two top stars, what I call the top stars in the keystone, because I call the narrow part at the bottom and the wide part at the top. If you made an isosceles triangle, if you remember your high school days, a perfect 90-degree or 360-degree angles make an isosceles triangle. Anyway, M92 would be perfectly triangular to the left-hand side of the keystone. Saying that, back to M13. What will I see? Well, you won't see this. This came off my telescope about a week and a half ago.
Nice.
It's a nice shot of M13. The globular cluster is just that. It's a glob of stars. They're coming together in a sphere. What you will see in your scope, if you look out, is it'll look like a fuzzy ball with a bright star on each side. And you'll definitely see it. You'll know it when you see it. You won't make out any individual stars probably with a pair of binoculars, but you'll make out that it is a globular, and you'll see the 2 bright stars on each side, and then it's almost in between the 2. Comparing it to the full moon, those 2 bright stars, one on each side, are about the width of a full moon. So it's a good size when you're looking through a pair of binoculars. You'll get a good view of it. It should be easy for you to see. That is our binocular target of the week. Recently in the newspaper, apparently a pilot put in a report that he was getting shot through the window with a laser on landing. So just a reminder that if you are using green lasers out there, make sure you know exactly what you're pointed at and use green laser safety. So, or you get this at the Star Party.
I like the Star Wars guys in the background there.
I do.
That's our bino target of the week.
We've done that, Mike.
We have.
Awesome. Thanks, Mike. Okay, we got Rosanna's fun facts. Paul, have we got time for that?
Yeah, I do. And
Okay.
But before we do, I noticed there was a question or two
Okay.
about what the filters, and there's just one of the ones that I did want to address.
Mm-hmm.
And it's from Jeff, and he says he has a question about the hydrogen alpha filter. I see that it's not for viewing the sun, but it can help with viewing the night sky in areas with high light pollution. Any thoughts? Okay, so basically, I have thoughts on that. First of all, when you're using hydrogen alpha in the daytime, you're using a filter to filter out the light down to that very slit of light that you want, that 656 nanometer wavelength. Then on the other end of the scope, you actually have a blocking filter. So there's a lot more going on when you're dealing with the sun than when you're doing nighttime photography. With nighttime photography, what hydrogen alpha filters are designed to do is the same sort of thing, but a much lesser degree, and it's more about color balance than it is about protection of light. And so when you're using a hydrogen alpha filter for night viewing, It wouldn't be for light pollution. It would be for accentuating the hydrogen alpha gases that you see in many of the nebulas that you see people taking picture of. That's what it would be for. Now, if you were going to use a filter for taking care of light pollution, you'd want to use a light pollution filter. And there are a variety of different filters that are designed specifically for light pollution. Some even get into the type of light that you're trying to negate. So that's the difference. So the hydrogen alpha for deep sky is using a filter to enhance the light for nebulosity. Hydrogen alpha for the sun is designed to cut in so you can see that particular wavelength of light. But in that telescope, there are many factors and components that make it safe to view it for observing. So those are the two differences. Jeff, I hope that answers that question.
Awesome.
And I think that was the only question I needed to answer. Oh, and Wayne Mansfield asked, he joined late, but he wanted to know, did he mention the pinhole projection? And yes, we did talk about pinhole projection, Wayne. If you want to review this on YouTube, you can actually wind it back, and there's a couple of slides actually we cover that topic as well. Okay.
Awesome. Great. Thanks, Paul.
Okay.
Okay. We're going from there to Rosanna. We are going to be probably 9:15, folks, before we sign off tonight. Hopefully, we can keep everybody interested here. So
we're running late.
That's okay.
It's a cloudy night. No sense going outside.
What are you going to do anyway?
I apologize.
No,
Okay, so
we like to talk.
Let's see if I can do this. All right. If I do this. Oh, good. All right. Now, the only other thing I got to do is this. When you know it.
I gotta start the music again.
This is the reason why we're late, because I don't know what the hell I'm doing. Okay. Now, let me just share my screen, or try to.
Paul Owen raised his hand. Okay.
Raised his hand, yeah.
I'm pressing things I shouldn't be pressing. Okay, share.
There it is.
Hey.
I want to make sure you can hear that.
I think we heard it.
We heard it. All right. Okay. Well, Rosanna writes, hi, Paul. There hasn't been as many days over the last few weeks where anyone could see their shadow. Here's hoping the clouds lessen and some sunny weeks are coming our way. On April 19th, NASA's Ingenuity, the little Martian helicopter, accomplished a huge feat. It became the first aircraft to complete a power-controlled flight on another planet. NASA's Ingenuity has hovered its way into history. Now, let me see which arrow I got to push to make this work. There we go.
There we go.
So here is a selfie of Ingenuity's own shadow, and the image credits through NASA, of course. Ingenuity rose 3 meters, 10 feet in the air, and remained suspended for 30 seconds before landing back on the red planet. Ingenuity followed up with a second higher flight on April 22nd. Now, one might ask, why is this such a big deal? It is an amazing task, even with the low gravity on Mars, flying is not easy. The Martian atmosphere is about 1/100th the density of Earth's, creating flight conditions similar to 30,000 meters or 100,000 feet above the Earth. This is an altitude that has never been reached by helicopters. So here's a quick look at Ingenuity's third flight on April 25th. And let's see if this will work. There it goes. So a fourth flight went exactly to plan, and Ingenuity remained airborne for 117 seconds and covered 266 meters. Now, NASA's, whoops. There we go. I lost my place. So now NASA's Ingenuity is working so well that it's transitioning it to Operations Demonstration Mission, and Perseverance will adjust the start of its mission to continue supporting the helicopter, which has rapidly become the star of the show. It was initially slated for a month of flight operations before Perseverance moved on, but now it could continue flying through late summer. Now, Ingenuity was designed with off-the-shelf hardware such as a Snapdragon 801 smartphone processor, so it doesn't have any bulky communication equipment to reach Earth. Instead, it relays data to Perseverance over the Zigbee wireless communication standard. So Perseverance has to stay close, which means it has not been able to start its planned primary science operations. Luckily, the team has found the region around Wright Brothers Field, the goal of the fourth flight, to be more interesting than expected. So Perseverance will trundle around there and do some science while it supports Ingenuity a little bit longer. And that would have been the slide here. So Ingenuity has one more flight in the technology demo phase, and the sixth flight in about 2 weeks will mark the beginning of the operations test. This phase will consist of longer one-way flights that sees the helicopter touch down near the rover's next parking spot. Along the way, it will continue to gather more flight data to inform the design of future flying explorers and make greater use of its surface observation and landing systems. These flights will pose a much greater risk, but the helicopter doesn't have long to live anyway. NASA will evaluate the results of the operations demo after 30 sols, Martian days, and Ingenuity's flight operations should be finished no later than August. That timing will allow the rover team time to wrap up its planned science activities and prepare for solar conjunction, the period in October when Mars and Earth are opposite sides of the sun, blocking communications. So interesting to note, although a helicopter has never reached 30,000 meters above Earth, on October the 14th, 2012, Felix Baumgardner launched from Roswell, New Mexico, and this is probably the coolest thing about this whole fact. I can just get it over here. And although from New Mexico, it has ascended 38,969.4 meters above the Earth in a helium balloon. He then jumped and became the first person to break the speed of sound in a free fall. Now, I actually have, at least I hope I do, the video of that. And let's see if that'll play.
Topaz Gigapixel AI uses revolutionary AI technology to accurately
commercials.
and
Stupid commercials.
enlarge your images up to
So wasn't that amazing? So as Rosanna wanted to finish up with on this one, she goes, I think I'll stick to following engineering's progress in making Earth-based shadows. Long live and prosper. Oh my gosh. So let me see if I can pull this off. I probably can't now. And that was this week's.
Rosanna's Fun Fact.
Thank you so much, Rosanna. That was
awesome.
Unbelievable. That was unbelievable. There we go. You're not on, Chris. Can't hear you.
Yeah, it was echoing back through.
Oh, okay.
Yeah, that's why I turned off my mic.
Isn't
Sorry.
that amazing?
Yeah, amazing.
You
Crazy.
imagine 100,000 feet.
100,000 feet.
And the guy, and he's going supersonic.
And just tumbling over end. Yeah.
And he straightened up just like Armstrong did. Remember?
Yeah. Exactly.
Then you got the guy he was talking to on the radio who did it 50 years prior to him with a lot less technology in his equipment.
Yeah, that's right. That was amazing. Incredible.
Crazy.
Yep. Brave boys.
Yes,
Okay.
sir.
We got a few photos to share before we sign off, so let me get to them just for a sec quickly. I'm going to start to, I want to get a few here, so we should be pretty quick. Oh, come up on the wrong screen, of course. Here we go. Bring it over this way. Oh, come up the wrong screen again. Hang on. My goodness.
Oh, I seem to come up on the right one. I saw it.
Come up the wrong way. Come up the wrong way. There we go. Do it this way.
Oh, it was sunset instead of sunrise. Okay.
Yeah, that's. So we get this photo from Kathy Adams. Actually, a few here. I missed the spectacular sunset last night, she said, catching barely the tail end. But when I get up at 5:30ish this morning, it looked adult to the west. Then she looked over to the east window and grabbed my camera bag and headed down to Oak Bay as fast as I could, and got there just in time for this. I think it was the most vibrant and beautiful pre-sunrise I've ever seen, she said. Yeah, it was incredible.
Some crazy skies lately.
Yeah, they've been absolutely wonderful. There's another shot from her.
Beautiful.
And the third one. Colors are just crazy. Yeah.
Well done.
She's also got these. She said, I was wide awake just before 5 a.m. I'm not sure what day this week was, but went outside. It was nice and clear and saw 2 bright stars. She opened up Stellarium and Sky Safari, and they were in the location both apps said Jupiter and Saturn would be. So I took my scope out and saw this and took a quick picture. I think it is Jupiter and 3 moons. Yes, it is. Actually, probably 4 in there. There were no details, but they would have been obscured by the sun, I'm sure. The picture quality is not good. It's cropped, and I did adjust the levels to better see. But I think you got them there, Kathy, so good job.
You got them. Definitely got them.
Nice work.
Yeah.
Yes. Congrats for your first view. Always fun to get that first view.
There it is.
Beautiful.
This is from Stefan Picard. Stefan says, here's my first shot of the Milky Way. You saw this week. I was up at 1:45 a.m. on Wednesday. I went outside and pointed the camera southeast. Settings on my Canon T1i were 15-second exposure at ISO 3200 and f3.5. Then a little processing to pump up the contrast, exposure, clarity, and tint. Then dragged down the highlights and shadows a little bit. This brings out great colors while keeping the darks fairly dark to contrast the pumped up brightness and colors extracted. All said about 3 minutes to process, so the camera does the bulk of the work if the settings are right on. Excited to add nightscapes to my astrophotography journey. Absolutely.
Awesome.
And
look at the colors.
This one came from Renat. Renat says, living in a beautiful place surrounded by nature and talented creatives is a true gift I cherish. Last night, nature painted the skies with great passion in Back Bay, Atlantic Canada. My painting in progress will be titled Curtain Call for the Stars. Luckily for us, she said, the drama was perfectly captured by my neighbor photographers Steve Cook and Gregory Eric Party, par excellence. Great shots.
Very nice.
And this is another one from Stefan. Sorry, I had these a little mixed up. This is another capture from his Milky Way shot.
Easy. Framed it so nice against that tree, eh?
That nice, eh?
Oh, beautiful. Beautiful.
Another one from Renat. These kind of went in the wrong order here, but there's another beautiful capture.
Yep.
And Stefan's final one here, I believe. Yep.
That's awesome.
Great shots.
Lovely.
Thanks so much for sharing all those. And if you wanted to send in your photos, just send them to Sunday Night Astronomy Show at gmail.com. And we love getting your photos, don't we, guys?
We do.
We do.
Absolutely.
Indeed. Thanks so much, everyone, for sharing those.
Keep them coming.
Well, great topics tonight. We had a good talk about safely viewing the sun. We had our talk about the Voyager spacecraft done. Bino Bud was in this to join us. We had Rosanna's excellent talk on ingenuity. And looks like we're ready to sign off. So not bad. 9:19. Well, we're a little longer, but oh well. We'll make up for it next week. No, we won't. Okay, well, so in closing tonight, folks, thanks again for your... I'll go to full screen. There we go. Thanks again for your continued support of our page. Thanks again to Rosanna for her continued contributions to our show. We really do appreciate all your efforts in helping us out there, Rosanna. Remember, too, we do love getting your photos, so send them into Sunday Night Astronomy Show at gmail.com, and we'll be happy to include them on our next broadcast. Or send them into my Facebook page if you like to. That's easy, too. We're also looking for suggestions for topics for future shows, so if you have anything that you would like us to discuss on a future episode, we are looking for topics all the time. We try to stay down. Usually after this broadcast, we'll sit and talk about what's coming up next week, and we just kind of look around the room. Paul does anyway. So, well, we'll do to talk about that. So that's where it kind of goes sometimes. Anyway, if you have anything that you'd like us to discuss on a future episode, please let us know. Please send your request to the same address, Sunday Night Astronomy Show at gmail.com, and we'll do our best to make it happen for you. Also, that if you enjoyed the content here tonight and you joined us from YouTube, please consider giving us a like and subscribing to our channel. And please let your family and friends know as well that we are here every Sunday night at the same time to help entertain and educate you on the night sky. So for now then, from Mike and Paul and I, stay safe everybody out there. We wish you all clear skies, and we hope to see you again here next week. And remember, as we like to say, guys, keep your scopes pointed up.
Yep. Yep.
Have a great week, everyone. Good night. Charlie Brown. Should we just let him go on? Thanks, everyone. Good night.